Hello everyone. Today, we would like to introduce our project, Application of QR Decomposition in MIMO Systems. This presentation explains why QR decomposition is important in modern wireless communication and how this is applied in MIMO signal detection. This is the outline of our presentation. We will first give a brief introduction to MIMO systems, then explain why QR decomposition is used, followed by engineering calculations and practical examples. Finally, we will discuss application scenarios and future direction of MIMO systems. By the end of this talk, we hope to demonstrate how a fundamental linear algebra concept like QR decomposition enable the high-speed 5G and Wi-Fi connecting we use every day. MIMO stands for multiple input, multiple output. In a MIMO system, the received signal is a combination of a signal transmitted from multiple antennas through the wireless channel. A practical example is a 5G base station, which may have hundreds of antennas to serve multiple users simultaneously while introducing interference. This massive MIMO approach is what allows hundreds of people in a crowded studio to all access high-speed internet at the same time. The MIMO system can be modeled as y equal to hx plus n, where x is a transmitted signal, h is a channel matrix, n is a noise, and y is a received signal. The main challenge of MIMO detection is how to recover XXX from this mixed signal efficiently and accurately. Because the signals are mixed together by the matching edge, we need a way to unmix them without also magnifying the noise N. QR decomposition helps simplify MIMO signal detection. First, it transforms the channel matrix into an upper triangular matrix, allowing syllables to be solved one by one instead of all at once. Second, it avoids matrix inversion, which is computationally expensive and power-consuming. Finally, QR-based detection provides better numerical stability and improves overall signal quality. For mobile devices, this means we can achieve a more stable connection while significantly extending battery life through faster, lower power computation. Starting from hx equal to y, we apply QR decomposition and write h equal to qr. By multiplying both sides with q transpose, the equation becomes rx equal to q transpose y. Since R is an upper triangular matrix, the transmitted syllables can be solved efficiently using back substitution. Because Q is an orthogonal matrix and R is 0 below the diagonal, the hardware only needs to perform simple division and subtraction, making the computing much simpler. In this example, we consider a 2x2 uplink MIMO system with two users transmitting simultaneously. The received signals and channel matrix are known. After performing QR decomposition, we solve the system step by step using back substitution. The final result showed that both users transmitted the signal value of 1. This practical demonstration proves how we can use this property of the QR matrix to isolate each user data from what originally looks like a massive mixed signal. MIMO technology is widely used in modern wireless systems. For example, 5G base stations use massive MIMO to improve spectral efficiency. Wi-Fi 6 use multi-user MIMO for faster and more stable connections. Satellite communication also adopts MIMO to improve transmission efficiency. In each of these cases, MIMO allows us to extend different signals to multiple receivers over the same frequency, boosting overall network capacity. Severe decoding is an advanced MIMO detection technique based on QR decomposition. Its goal is to achieve near maximum likelihood detection performance without exhaustive search. By using the upper triangular matrix R, the detection problem becomes a tree search process. A pruning strategy discards unlikely branches, sufficiently reducing computational complexity and making high-order MIMO system practical. By only searching within a specific sphere radius, we avoid checking every possible signal combination, which make high-speed communication feasible. Zero forcing is the most instituted interference cancellation method. Although it can be expressed as x equal to h inverse y. Direct matrix inversion is unstable and amplifies noise. Using QR decomposition, ZF can be implemented by solving Rx equal to 2 transpose y without computing the inverse. This method is highly efficient and suitable for FPGA and ASIC pipeline implementation. This QR-based approach avoids the stability issue of the reverse inversion, providing a much cleaner signal for hardware processing. MIMO systems are evolving from 5G massive MIMO towards 6G XL MIMO. Future systems will focus on near-field beamforming, cell-free architectures, and intelligent reflecting surface. These developments require low complexity and hardware-efficient algorithms, making QR-based detection techniques even more important. In conclusion, QR decomposition played a crucial role in MIMO signal detection. Advanced detection techniques such as QR-based zero forcing and severe decoding will continue to be essential for reducing complexity in future massive MIMO systems. These are the references we use for this presentation. Our research is built upon fundamental works in wireless communication, includes IEEE's Insight on Massive MIMO and Technique paper from Cornell University and St. Daniel State University on hardware efficiency QR decomposition. These resources illustrate how mathematical theory is translated into the physical circuit of our mobile devices. We would like to conclude by emphasizing that while the math behind QR decomposition has been known for a long time, its role in the future 6G and beyond is only just belongings. Thank you for your attention.